Fault tolerance is the property that enables a system to continue operating properly in the event of the failure of or one or more faults within some of its components. If its operating quality decreases at all, the decrease is proportional to the severity of the failure, as compared to a naively designed system in which even a small failure can cause total breakdown. Fault tolerance is particularly sought after in high availability or life-critical systems. The ability of maintaining functionality when portions of a system break down is referred to as graceful degradation. A fault-tolerant design enables a system to continue its intended operation, possibly at a reduced level, rather than failing completely, when some part of the system fails. The term is most commonly used to describe computer systems designed to continue more or less fully operational with, perhaps, a reduction in throughput or an increase in response time in the event of some partial failure. That is, the system as a whole is not stopped due to problems either in the hardware or the software. An example in another field is a motor vehicle designed so it will continue to be drivable if one of the tires is punctured. A structure is able to retain its integrity in the presence of damage due to causes such as fatigue, corrosion, manufacturing flaws, or impact. Within the scope of an individual system, fault tolerance can be achieved by anticipating exceptional conditions and building the system to cope with them, and, in general, aiming for self-stabilization so that the system converges towards an error-free state. However, if the consequences of a system failure are catastrophic, or the cost of making it sufficiently reliable is very high, a better solution may be to use some form of duplication. In any case, if the consequence of a system failure is so catastrophic, the system must be able to use reversion to fall back to a safe mode. This is similar to rollback recovery, but can be a human action if humans are present in the loop. A highly fault-tolerant system might continue at the same level of performance even though one or more components have failed. For example, a building with a backup electrical generator will provide the same voltage to wall outlets even if the grid power fails. A system that is designed to fail safe, or fail secure, or fail gracefully, whether it functions at a reduced level or fails completely, does so in a way that protects people, property, or data from injury, damage, intrusion, or disclosure. In computers, a program might fail safe by executing a graceful exit as opposed to an uncontrolled crash in order to prevent data corruption after experiencing an error. A similar distinction is made between failing well and failing badly. Fail deadly is the opposite strategy, which can be used in weapon systems that are designed to kill or injure targets even if part of the system is damaged or destroyed. A system that is designed to experience graceful degradation, or to fail soft, used in computing, similar to fail-safe, operates at a reduced level of performance after some component failures. For example, a building may operate lighting at reduced levels and elevators at reduced speeds if grid power fails, rather than either trapping people in the dark completely or continuing to operate at full power. In computing, an example of graceful degradation is that if insufficient network bandwidth is available to stream an online video, a lower resolution version might be streamed in place of the high-resolution version. Progressive enhancement is an example in computing, where web pages are available in a basic functional format for older, small-screen, or limited capability web browsers, but in an enhanced version for browsers capable of handling additional technologies or that have a larger display available. In fault-tolerant computer systems, programs that are considered robust are designed to continue operation despite an error, exception, or invalid input, instead of crashing completely. Software brittleness is the opposite of robustness. Resilient networks continue to transmit data despite the failure of some links or nodes. Resilient buildings and infrastructure are likewise expected to prevent complete failure in situations like earthquakes, floods, or collisions. A system with high failure transparency will alert users that a component failure has occurred, even if it continues to operate with full performance, so that failure can be repaired or imminent complete failure anticipated. Likewise, A fail-fast component is designed to report at the first point of failure, rather than allow downstream components to fail and generate reports then. This allows easier diagnosis of the underlying problem, and may prevent improper operation in a broken state. If each component, in turn, can continue to function when one of its subcomponents fails, this will allow the total system to continue to operate as well. Using a passenger vehicle as an example, a car can have run-flat tires, which each contain a solid rubber core, allowing them to be used even if a tire is punctured. The punctured run-flat tire may be used for a limited time at a reduced speed,